Section 4.20, Semiconduction. There are two types of semiconductors, intrinsic versus extrinsic. In intrinsic semiconductors, the gap between the valence band and the conduction band is small, smaller than 4 electron volts. So it's possible to promote electrons from the valence band to the conduction band by simply heating up this semiconductor. And now we have free electrons in the conduction band, and we have holes that can move freely in the valence band. And that's why semiconductors can have fairly decent conductivity at higher temperatures. They are also called semi-metals because they have a fairly small band gap. Now let's look at extrinsic semiconductors. For example, if we dope this silicon with phosphorus, remember phosphorus has 5 valence electrons. Silicon has 4 valence electrons. So if you have just pure silicon, you have a valence band, a conduction band, and a fairly large band gap here. Now, adding phosphorus will introduce a new dopant band because of the 5th valence electron from the phosphorus. Where do we put this additional electron? It's right here. Right? Phosphorus can form another dopant band here. And now let's look at the gap between the filled orbitals and unfilled orbitals. This gap is now much smaller than the original band gap of pure silicon. So now this semiconductor can have much higher conductivity because of this much smaller band gap. And similarly, we can introduce borons into pure silicon. A boron atom has only 3 valence electrons, one less than silicon, and therefore we have additional acceptor band. So this is actually unfilled orbitals from the boron atoms. And because this unfilled orbitals lay only a little bit higher than the valence band of silicon, again, it's very easy to promote electrons from this valence band of silicon to this empty band formed by the boron atoms. So by heating up this doped silicon, boron-doped silicon, electrons can be easily promoted from here to here. Again, this is the new band gap. This is much smaller than the band gap in a pure silicon. And now with electrons in this boron acceptor band and also some holes in the valence band of silicon, this semiconductor can have fairly good conductivity now. Now let's look at another type of semiconductors. First, let's look at metal oxide. Usually it's a very good insulator because the gap between the valence band and conduction band is very large. It's larger than 4 electron volt. So this metal oxide does not conduct electricity. But now let's introduce some defects. What if we have fewer oxygen atoms or fewer metallic atoms? When we have fewer oxygen atoms, we have excessive metals. And those excessive metals can form a band here. Now, these electrons can be easily promoted into the conduction band. We have a semiconductor now. Again, if you have 1-to-1 ratio between zinc and oxide, it's an insulator. But if you have oxygen deficiency, then you have excessive zinc atoms. The excessive zinc atoms can have excessive s electrons from those zinc atoms. They can form this band here very close to the empty conduction band. That will dramatically reduce the band gap. This is the new band gap, much smaller than the old band gap of 1:1 zinc oxide. So this is now a semiconductor. Also, we can have fewer metals. In that case, we have excessive oxygen atoms. They can form a additional acceptor band here. It's unfilled, and it's just slightly higher than the previous valence band. So again, now we have a smaller band gap. So from here to here, this is a very small band gap. It's easy to promote electrons from the valence band to this new acceptor band due to this defects. And now this is also a semiconductor.